All right, Calculus 12, here's some information on inverse trig functions. So I'm going to go to Desmos first after we look at the title here. So this is in the trig section of the textbook. I usually do this every year. This year with the school not being on, I'm making this optional. So here it is with Desmos. I'm going to show you some information. So if you go to Desmos, here's the sine function. Now, the sine function is y equals sine of x. If I did x equals sine of x, it would do the inverse of this and reflect it over the line y equals x, and you would end up with this graph, which would basically be the sine graph going upwards. That, unfortunately, does not pass the vertical line test. So what they decided to do was to make this a function. They decided to keep as much as the function as they could, or as much as the relation as they could, to make it a function. And what they decided is here's the true inverse relation. This is the inverse function. And when I click on this, here's the part. I don't know if you can see that color. See the green on top of there? I'll get rid of it. That's the part of the graph that they decided to keep. And that is between, if I zoom in, whoa, that is between, or we'll talk in a minute, that's going to be between the intervals of the y-axis between pi over 2 and negative pi over 2. All right, for cosine, here's cosine graph as you know it so well. The inverse relation is this, okay? And here is the part of the graph they kept. To show again, of the inverse cos, that's the part that they kept for the function. And we'll talk in a minute, that's between 0 and pi on the y-axis, because now it's on the y-axis, it's been flipped. And for tan, same thing, there's your tan function as you know and love it. Here's the inverse, this gets messed up, right? There's the inverse, which is not a function, and what they decided to keep for the function of that was this portion. So that's the portion that they kept. That is the arctan. And they call it either inverse tan, arctan, or they use the -1 button. Remember, that has nothing to do with an exponent. So, some weird facts with these guys. Because they have so many troubles with the actual true inverse relation to make it a function, there has to be major restrictions. And that's what makes these guys a little bit of a gong show. So here we go. The theory behind this is, you know the regular sine function, the inverse sine function, then remember a few things with this inverse sine. The number going into the inverse, or arc sine, is a ratio. The number that's coming out is the angle, and the angle they decided to limit it at was between -90 and 90, negative pi over 2 and pi over 2. So basically this function is only allowed to spit out answers in quadrant 1 and quadrant 4. So 0 to 90 and 0 to -90. For cosine, unfortunately, it couldn't keep it the same. It has angles between 0 and 180, or 0 and pi. So it's in quadrants 1 and 2, just the way it works. And arctan, or inverse tan, is the same as inverse sine, except that pi over 2 and negative pi over 2 are not included. All right? So that's really important to keep in mind. That's the weird part of these are functions that have limitations. And for me, I need to know those limitations. And the second thing I always have to remind myself of, and it's really important, is these arc or inverse functions for sine, cos, and tan take in a ratio and spit out an angle. I have to always remember that the output of these is angles, completely the opposite to what your sine, cos, and tan are. So here, this takes in an angle and spits out a ratio. That's really important to kind of get your mind in the right mindset. So here are some examples that we're going to go through, which are nothing to do with calculus, but it is a stepping stone to the derivatives of these, which are needed in calculus. So someone wants you to find the exact value of this. Obviously, I could go to my calculator and go, inverse sine or second sine of root 3 over 2 and it would spit out an answer and it'd be like, okay, there it is. But for me as a mathematician or as a human, I need to know where it's coming from. So how to analyze this? First of all, as soon as I see inverse sine, I have to think to myself, the output of this is only allowed to be between -90 and 90. So right away, I know the answer is either here or here. It can't be in those two quadrants, okay? So I know this is taking in a ratio, it's gonna spit out some angle. All right, and that angle has to be in quadrant 1 or quadrant 4. That is it. Okay, and it's gonna be, I'm gonna put here, has to be between those restrictions. That's the only part you have to remember, but when I say only, I mean that takes a little bit of thinking. So then next thing is, okay, if I were to rewrite this into the other form, this would be the same thing as saying sine theta equals root 3 over 2. And as soon as I see root 3 over 2 for sine from my trig table, right away the bells and whistles should go off as far as the reference angle for this with my table of values with root 3 over 2 would be pi over 3. All right, and then I would ask myself, is pi over 3 in this quadrant? Well, is it this quadrant, the all suckers take cocaine? Is it in the all or the cocaine or the cosine? Well, I know it can't be in quadrant 4 now because first of all this is positive. So I know right away that rules out this quadrant for sine. So it must be in quadrant 1. So the angle that this spits out must be pi over 3 or 60 degrees depending on, but they didn't ask what to answer in, so you always answer in radians. Seems easy in a way, like it's almost like duh, I knew that, but you'll see how these get a little bit sneaky as we go along. So what about the inverse cos of the cos of 7 pi over 6? Intuitively, if you were just a person who was thinking mathematically, like really logical, you might just think these are inverses of each other. So why isn't the answer just 7 pi over 6, which might be the logical answer? But inverses start to play a little bit of trouble because this guy is only allowed to spit out angles between 0 and pi. That is inverse cos's restrictions on what it outputs. So I now know the answer for theta is either, what I'm looking for is either here or here. The next thing would be I need to figure out what is it taking in to spit out one of these values. Because either the answer is this or it's that. I don't know yet. And it's one of the two, because remember this is a function. There is not two answers here, it's only one. So now what is cos of pi, 7 pi over 6? Well, that's just a regular question of this is going to spit out a ratio. This I know is in quadrant 3. So that angle is in quadrant 3, 7 pi over 6, with a reference angle of pi over 6. Cos of pi over 6, which is cos of 30 degrees, is root 3 over 2. Also, root 3 over 2 in this quadrant, all suckers take cocaine, it's going to spit out, so cos of 7 pi over 6 spits out a negative root 3 over 2. So I could replace this whole argument with arc cos, inverse cos. This whole thing spits out a negative root 3 over 2. And then I'm back to the same journey of, okay, the reference angle I know for root 3 over 2 for cos is pi over 6. But it's negative. Which one of these two quadrants spits out a negative ratio? And that right there tells me it's not this quadrant, it must be this one. So my answer must be here, where this is a pi over 6. The actual answer I'm looking for is this amount, which is pi minus pi over 6, which is actually 5 pi over 6. That's weird. So the answer to this is actually 5 pi over 6. Like there's one that is not, that is sneaky. Okay? So that's why we're going through that, is the sense of it's these little sneaky little tricks here that we got to be careful with. Next guy. How do we deal with one like this? Tan of sine inverse of 3 over 5. Well, for me, I really have to think about this for a minute. First of all, I'm going to analyze what is this even going to be spitting out? So I kind of work from the inside out. So what does inverse sine take in? Oh, that's a ratio. Okay? This is a ratio right there. When inverse sine takes in this ratio, this whole bit inside spits out an angle. And then when the angle goes into the tan, that's going to ultimately spit out a ratio. So in the end, I'm going to get a ratio, but I have to think about this in layers. So let's look at this. Let's focus on this angle here. Let's call this theta. Theta is that. So now I'm like, okay, I don't really work with this well. I'm going to rewrite this. Before I rewrite it though, I want to keep in mind arc sine, inverse sine is only allowed to be here and here. So I'm going to keep, I know it's in quadrant 1 or quadrant 4. I'm going to keep that in my back pocket. I'm going to rewrite this as sine theta equals 3 over 5. Okay? Now the fact that I've got a positive ratio means out of these two quadrants for sine, this one's out. So I must be in quadrant number 1. This must be theta, which I don't know yet, but I know the ratio. This is y over r. This is 3, this is 5. So there's my y, there's my r, my x with Pythagoras must be 4, 3, 4, 5 triangle. Once I have all that information, knowing that even though I don't have the angle, I know the angle is represented by this picture. And then if I ultimately want this, because remember I replaced that with theta, that picture tells me what tan theta is without even knowing what theta is. So tan theta, according to that picture, is 3 over 4. Opposite over hypotenuse, y over x. Now you might argue, well, why didn't I just go to a calculator and type that in? Well, yeah, I could have. I could have just went tan, am I in radian mode? Yep. So tan of inverse sine of 3 divided by 5. And yeah, I could have got the answer, but then you know what? I'm not really thinking then, but at least I know where it's coming from now. All right? Next guy. Same kind of thing. I've got this weird mess inside this sine. So this is going to spit, sine is going to spit out ultimately a ratio. I've got a 2 inside the sine that's multiplying this. This here is a ratio. Arc cos spits out an angle. So I'm going to rewrite this because I'm going to let theta equal arc cos of negative 4 over 3. And then I can rewrite this as sine of 2 theta. That makes it a little bit better on my eyes, but now I'm still upset with the theta. But I have something similar to this last question. I can look at this and say, oh, arc cos, I know spits out angles between 0 and pi. Okay, so I'm in quadrants 1 and 2. It's taking in a negative ratio out of these two quadrants. Which one is cosine negative in? This one. So I know it's in quadrant 2. And I also know if I rewrite this in a better form, this is the same thing as cos of theta equals negative 4 over 5. And now the angle that I'm looking for is this, with the side length being, remember this is x over r, this is 5, this is negative 4, hence this has to be positive 3. And there's my x, there's my y, there's my r. And if these didn't work out to be a 3, 4, 5 triangle, I would just use Pythagoras to find the missing side. And now, once I have that information, I could then maybe find the double angle, but the trouble is I can't just double this angle. Here comes my trig identity. Remember, sine 2 theta is the same thing as 2 sine theta times cos theta. And that picture tells me both of these values. Well, first of all, cos theta is right there. It's 4 over 5. Sine theta, according to the picture, is y over r, 3 over 5. And again, I can just replace sine theta with 3 over 5, its ratio, cos theta with negative 4 over 5. And then multiply that all together and I get negative 24 over 25. Which again, I could have just typed all of that in. Yeah, good for it. Times arc cos of -4 divided by 5. And got that number, which is -24 divided by 25. But again, I wouldn't have known anything about that. Last one, just a little limit question with a little arctan thrown into it for the fun of it. So how would I go about analyzing this? Well, from a limit point of view, I wouldn't know to graph that very easily at all, okay? If it was just arctan, remember, just arctan itself, I should know that graph now. So I'll keep that in my back pocket. But unfortunately, it's not just an x inside, it's just 1 over 2 to the x, which makes this not this graph. So what I will do, I will try, again, I gotta be really careful with this. I gotta try to think about this logically and make sure every step of the way I'm thinking about this in a good way. Can I muster my human brain to understand what this would be? Well, remember, this is a negative exponent. Negative exponent, I can just rewrite this as this. And what's 2 to the infinite power? That's infinity. So now I've got infinity as the input to this tan inverse. And I have the graph of tan inverse. What happens as x goes to infinity? This y value here, this upper horizontal asymptote in the inverse is actually y equals pi over 2. So this will get closer and closer and closer to pi over 2. Weird. But we're getting into weird stuff. Cool stuff, actually. So that is it for inverse trig. Notice there was no derivatives, a little bit of limits, but most of it was evaluation, just getting used to the function's limitations. Okay, have a good one.